Alright, hey everyone. So welcome to our next section. We're going to run through, it's called Stoichiometry, and it's going to lead us kind of into the, a little bit of stuff in connection with moles, balancing equations. It's going to bring a few different concepts together. So to start off with, I'd encourage you to jot down the notes along the way, pausing the video wherever you can, just so you can kind of copy the notes down as we go through them. When we get to any example problems, pause the video, try out those example problems, and I'll give a little pause in the video at that point, and then try out the question, and we'll go over the answer to that problem together. So for stoichiometry, it's a balanced chemical equation. So we've worked on balancing equations prior to this unit, so it should be something that you should be a little bit familiar with. It's a balanced equation that provides the same kind of quantitative information that something like a recipe or materials list does. So it basically gives us an idea to say how much we need of something if we're doing a chemical reaction. So for example, the components to a tricycle, for instance, would be things like the frame, and if we call the frame the capital letter F, then we'd have the seat, S, we'd have the wheels, W, the handlebars, H, and the pedals, P. So from the materials to production, it would be like going from reactants to products. We come up with all the materials we need, and then when we put them all together, we get a product at the end. So if we were to visualize this, we'd have one frame, we'd have one seat, we would have three wheels, right? So we'd have to take a 3 in front of that W. We'd have handlebars that are there, we have 2 of those, and then we have a pedal. So if we were to go down here, we can see we've got the frame, the seat, we've got the 3 wheels, we've got a handlebar, and then we've got 2 pedals. And if we were to combine those together, we'd go from reactants to products. So start off with our reactants, and we would get our products in the end. So we can see that combining these things together is like a materials list making a final product. So if we were to use a balanced chemical equation, we use it to calculate how much reactants are needed or how many products are formed in a reaction. We can use this kind of similarly to how we would have used moles in a previous section. So this can also be done to save time and money depending on what's being produced, because they can predict how much of a certain product we might need to order in order to do a reaction or an experiment. So the calculation of quantities in chemical reactions is a subject in chemistry called stoichiometry. They're based using balanced chemical equations. We've used that a few times now, so your equations always need to be balanced. And then after that, we can start to compare these things together. So as an example, it's here in a 5-day work week. We've got this tiny tyke is scheduled to make 640 tricycles, and it's asking how many wheels should be in the plant on Monday morning in order to make them. So specifically, how many wheels would you need to make 640 tricycles? Now, I'll get you to kind of figure this out first, and then I'll show you the kind of the chemistry way of setting it up. So pause the video, give it a try, and come back when you're ready. All right. So if we started off, we know what we're looking for. And first we'll write it out using kind of the words that we've seen from before. So we have 640 tricycles. And in each tricycle, here's where we need to set up that chemistry part. So we have tricycles, and then what I need to see is how many wheels. So I need to cancel tricycles out. Now, this is kind of that approach that you would have seen with moles, where we're trying to cancel out units top to bottom. So we know in every one tricycle that there are 3 wheels. And so I can see that my tricycles are going to cancel out. And what's left is 640 times 3 with wheels as the unit. So that gives me 1,920 wheels in total. Now, I could simplify this slightly, and instead of saying tricycles, we could start to use that symbol part that we had from before. So we know a tricycle, and this is going to be the exact same thing, just showing it in a little bit different of a way. I've got F for the frame, S for the seat, W3 for the wheels, I had H for the handlebars, and then I had 2 pedals. And so we know that there are 3 wheels in every one tricycle. That was FSW3HP2. And then again, they'll cancel out because that's like the symbols for what a tricycle stands for. And I'm left with 1,920 wheels. All right, being the same thing. All we're doing is just getting rid of the words, and we're just starting to get that idea of using symbols in their place. So we can interpret chemical change in the same kind of process. And in a lot of our examples, we're going to use this equation, which we start off with nitrogen gas, and we add hydrogen gas, and it gives us ammonia, which is widely used in fertilizers. Okay, so the formation of ammonia would look like this, and we can see we have a balanced chemical equation to start off with. Okay, so this balanced equation can now be interpreted in terms of different quantities, like numbers of atoms. Okay, we can look at the numbers of atoms of each one of them, we can look at their molecules, or we can look at the number of moles, we can look at its mass, we can look at its volume. We can start to compare reactants to products in all kinds of different ways here. So the number of atoms at the atomic level, the number and type of atom before the reaction are accounted for after the reaction. So if we were to look at our equation, and I were to count atoms, I can see I have 2 nitrogen atoms on the left, and I have 2 nitrogen atoms on the right, in the reactants and the products. So I can say the same thing with hydrogen, in that there are 6 atoms on the reactant side and 6 atoms on the product side. So atoms are accounted for before and after the reaction. Now the number of molecules, for instance, the ratios formed by these balance equations can be scaled to larger numbers while still making the same compound. Because these numbers are quite small, then Avogadro's number can be used to scale them to larger values for whatever we would need. So we can take a look at the number of molecules that are present in each one and start to understand how many are there. Avogadro's number, remember, 6.02 times 10 to the 23. We can use that to start to count representative particles. In this case, those representative particles stand for molecules. If we take a look at the number of moles in a reaction, they're the coefficients. So the total number of moles in the reactants don't necessarily equal the total number of moles in the products. Now, we haven't really talked about moles in terms of the equations where they're at. We've referenced moles several times over when we did the moles unit and converting back and forth, and we're going to bring that part back into here as well. So moles are just the numbers in the front of a balanced chemical equation. If we take a look at the mass, okay, the balanced chemical equation obeys the law of conservation of mass. So if I add up the mass of the reactants and the mass of the products, they should be the same. And lastly, if we take a look at the volume, if we can assume standard temperature and pressure, like STP, then we can use this idea of 22.4 liters as the volume per mole of any gas. So we're referencing kind of molar volume here. 22.4 is the same unit that we would have used previously in the moles unit. So after that, we've got the mass and conservation in chemical relationships. So mass and atoms are conserved in every chemical reaction. The other ones are not. When we went through that list of 5 different things there, mass, the same amount of mass is in the reactants as it is in the products, and we did the same thing with counting atoms. But molecules, formula units, and formula units would have been referenced in that previous slide as could have been moles, could have been molecules. Okay, molecules could be atoms based on what's there. It's just kind of what we're referencing in terms of representative particles. The volume isn't always conserved, although it can be. It just depends. It's more of a coincidence than it is a set rule. Okay, and that's it for that one. And so, just as an example, at the end here, we've got hydrogen sulfide, which smells like rotten eggs, is found in volcanic gases, and we have a balanced equation for the burning of hydrogen sulfide. Okay, so we can see our balanced equation. Let's here. We've got 2 and then H2S as a gas plus oxygen gas gives us sulfur dioxide and water as a product. So what the question is asking us to do is it wants us to express this in terms of the number of representative particles and the number of moles. And then after that, it wants us to prove this law of conservation of mass by finding the masses of the reactants and the products. And they should match up to be the same. So I'd like for you to pause the video. I'd like for you to try A and B, see how you do, and then come back when you're ready to go through it. All right, so let's take a look and kind of see how we can make this work for us. So in A, it wants us to show the number of molecules. So we can start off, and really all we're doing is just writing it out. We're saying what number of molecules are present for each one. So we have 2 molecules of H2S. And we're going to add that to 3 molecules. So if you notice, I'm just using the coefficients here because they're just stating how many molecules of the compound we have. 3 molecules of O2. And then that's going to give us 2 molecules of SO2 plus another 2 molecules of H2O. Now, after that, we need to say the number of moles. Well, remember that the moles, in this case, are going to match up the same as the molecules, and that they're the coefficient numbers in the front, right? Moles are like the amount of ingredient that we need. So, in this case, all I would say now is that I have 2 moles of H2S, and I have 3 moles of O2, and that's going to give me 2 moles of SO2 plus 2 moles of H2O. So it's just a different way of looking at it. And here I just wrote the shorthand term for moles there. You could put MOLES, but that's just kind of the abbreviated version. Okay, but all we're doing is just taking the coefficients and we're just kind of saying almost in words what's happening, right? Like how are we getting from reactants to products in that balanced equation. Now B is a little bit different. B is asking us to find the number of grams for each one of these things, so the molar mass of them. Okay, and we want to compare the reactants to the products. So I'm going to use my previous step in order to go through this, and we're just going to break apart each one of them and find their molar mass. So we have 2 moles of H2S, and we're going to multiply that by its molar mass. Now here's where we have to remember a little bit of stuff about moles from this previous unit that we did. So if I have moles on the top and I want to convert it to grams, then I need moles on the bottom to cancel it out. Okay, after that, I'm just multiplying them through, and the molar mass is saying that in 1 mole of H2S, I have whatever the molar mass is from the periodic table. So if I take 2 hydrogens and 1 sulfur and add them together, I'm going to get 34.09 grams of H2S. So that's how many grams are in 1 mole of H2S. Now I can see moles on the bottom and moles on the top are going to cancel, and really I could just take 2 times 34.09. It's going to give me 68.18 grams of H2S. Now I'm going to go through the same kind of process with each one of them. So 3 moles of O2, same thing here, 1 mole of O2 has a molar mass of 32.00 grams of O2 because it's 2 oxygen atoms, each one is 16. The moles of O2 are going to cancel, and I'm going to get 96 grams of O2. Okay, those are my reactants. And so together, if I were to add these up, I'm getting 164.18 grams of reactants. Now I'm going to go through and do the exact same thing, but now we're going to take a look at the products. So I've got 2 moles of SO2, and same thing, in 1 mole of SO2, it has a molar mass of 64.07 grams of SO2. The moles are going to cancel, top and bottom, and when I multiply these two together, I get 128.14 grams of SO2. Then I'm going to go and do the last one, which is H2O. We've got 2 moles of H2O. And same thing for the molar mass. In 1 mole of H2O, we get 18.02 grams of H2O. Moles of H2O we're going to cancel, and this thing's left with 36.04 grams of water. And then if I take a look at this one and add these two together, then I get that same 164.18 grams of products. Okay, and then we can see back and forth as like a final statement, because I had the same value at 164.18 for each of them, that mass is conserved. So, different ways that we can express different reactions, different components, and that's just kind of our starting point for stoichiometry. So I have a couple intro questions for you to work on. They're 1 through 10, 355 to 338 out of the textbook. And if you have any questions, please let me know.